Linear dielectrics. This is starting on page 185 of the text. So last week we talked about dipole moments, and we mentioned that this quantity right here, big P, is the dipole moment per unit volume. Under normal conditions, if a material is not exposed to an electric field, it will not have any net dipole moment. There are exceptions. Crystals of polar molecules will have a built-in dipole moment. But in general, for most materials, no electric field means no dipole moment. We can induce dipole moments and therefore net polarization in a material by applying an electric field to it. We can apply a Taylor series to this and say that for very small electric fields, the polarization is therefore linear with electric field. Now again, this is not always the case. It is especially common to have materials that have polarization that depends on the cube of electric field. But we are not going to get into that in this class. So for today's lecture, we are going to assume that materials follow a linear polarization model, where the polarization of the material is equal to some constant times the electric field. This K is just generic constant. It's not the Coulomb constant or any other named constant. Now, because of the units involved, we often see this linear relationship written like this, where the polarization is equal to the permittivity of free space times this quantity right here, called the electric susceptibility, times the electric field. Just to clarify, this letter is not X, it's the Greek letter chi. If you call it X, I'm not going to worry. Chi. Writing it like this, chi is known as the electric susceptibility, and it is a dimensionless quantity, which means that we can just give materials numbers. Now, if you'll recall, the relationship between the electric displacement, electric field, and polarization was this formula right here. Electric displacement is equal to epsilon naught times E plus P. Well, if P is written out in this form, then we can say that the electric displacement field is equal to epsilon naught times this quantity, 1 plus chi, 1 plus the electric susceptibility, times the electric field. In this textbook, you'll often see this term 1 plus chi e as epsilon r, called the relative permittivity. When you took physics 2, you might have learned this as kappa, the dielectric constant of a material. It's the same thing. And then finally, we can combine these two terms to say that the displacement field is equal to just the permittivity of the material times electric field. So we now have three ways of describing the properties of the material. We have the electric susceptibility, we have the relative permittivity, and we have the material permittivity. Now, in the last lecture of last week, I pointed out that the electric displacement field does not follow many of the properties that the electric field does. Namely, it cannot be described by a potential function because it did have a curl. However, if we are describing a material with a linear polarization, then we can say that the curl of D is equal to the curl of this term. Epsilon naught is a constant, so we can pull it out. And if you look at the front of the text, vector identity number 7 says that we can replace this with ER times the curl of E minus E cross the gradient of epsilon R. Again, if we are dealing with the case of statics, the curl of E goes to 0, so this term goes away. And if we are dealing with a material whose relative permittivity is not changing, which is a very common case, then this term will go away. Which means that as long as we are in a material with a constant dielectric constant, then the curl of D does vanish. And D can be described by a number of the shortcuts that we learned for E. Now, if there is a charge, and I would like you to look at figure 4.22 on page 189. If there is a charge in a free charge inside of a dielectric, we can model it as having a net charge that is decreased by the factor of 1 over 1 plus key E, or 1 over epsilon R. The reason why it is decreased is, again, looking at figure 4.22, you see that if there is a positive point charge placed, it will tend to polarize the material around it, which will create a charge of the opposite sign directed towards our point charge, with the displaced charge, or with the countering charge farther away. And that effect, it will appear as though the charge inside that place charge is smaller than it actually is when calculating purely electric field. However, as the textbook notes, this is a relatively unusual circumstances. Typically, when we're dealing with a material, we place charge on the surface. For that, I would like to reference equation number 4.41 on page 192. This quantity, epsilon, so this is the epsilon of the material in question, times partial V partial N. This is a fancy way of saying the normal component of electric field. If you're at a surface between two dielectrics, you'll have one value of epsilon and one value of dV dN on top, and a different value of each on the bottom. The difference between those two quantities is given by the free surface charge. So the surface charge not induced by the polar moment, but the free surface charge, the surface charge that we would otherwise, or that we would place separate from the problem.